So yes, as you mentioned, we're here to talk about the Clean Power VFD, um, and I will aim to present for about 30 minutes, and then we'll have 15 to 20-minute questions. We're a small group, so if someone has a question, feel free to raise your hand in the Zoom, um, and I'll let you know either I'll address it right away or we can see it a little bit later. So, of course, everyone who is on the call, I'm sure knows very well VFD, and I will try to skip parts on VFD theory and keep it to a minimum and really focus on the value add of the clean power VFD. But to make sure we all have the same background, let's remind ourselves that VFDs are there because of their tremendous benefit, whether it's a process focus, its reliability for motor, or of course, energy efficiency. But outside of these benefits, they also come with disadvantages that need to be mitigated. And we can put those into two broad categories. Um, Impacts on the grid, mainly harmonics, and impacts on the motor coming from the pulse width modulation, as you've seen in the quick video. And SmartD's mission, really, since our inception in 2018, has been to create a VFD that addresses both the disadvantages on the grid and on the motor. So a truly filterless VFD with low harmonics on the grid and a pure sine wave to the motor. We're going to keep the agenda very straightforward. So we'll talk about the grid side, we'll talk about the motor side, then we'll talk about the technology behind the Clean Power VFD, and we'll conclude by talking about the product and where it can have a maximum impact. Throughout the presentation, I'll talk about the VFD reality of today. I'll refer to some lab results. Those were done by third-party lab where they had dedicated motor test bench with long cables, about 500 feet, a dedicated transformer to mimic a very stiff grid, and comparing our Clean Power VFD, a standard 6-pulse drive from a leading manufacturer, and that same 6-pulse drive with passive harmonic filter and sine wave filter. And then I'll refer throughout the presentation to different field results and case studies. So let's dive into it right away, focusing on harmonics to start off with. Harmonics, to understand where they come from in a VFD, we just need to remind ourselves of the VFD architecture. 3 parts to the VFD: the diode bridge rectifier, the DC bus, and the inverter. In the case of grid side harmonics, they're mainly caused by the diode bridge, where in this case, it is letting current through only when the voltage is high enough to charge the DC bus. This means that in between these little humps, you have 0 current draw. And so you're having a nonlinear draw on the grid, and that is the core source of your harmonics. And so typically in a 6-pulse drive, you'll have harmonics around 30, 40%, even more if you don't have an integrated DC choke. And the impact for you is you can have interference with sensitive equipment, you can have a poor power factor, but more importantly, the core impact of of harmonics is overheating of equipment. So if you have a transformer, a UPS, all of these need to be oversized because that harmonic content needs to be dissipated as heat. And of course, you also have standards. So in North America, it's IEEE 519 that might mandate you to keep that harmonic content low so that you don't start polluting other equipment on the grid with your own harmonics. Typical mitigation, as you know, line reactor or harmonic filter. Let's look right away how a harmonic filter compares to a SmartD Clean Power VFD. So here you can see that in the middle, in your middle screen, you have your standard 6 pulse without any filtering. And you can clearly see the current draw that is nonlinear, and that's the cause of your harmonics. If you're putting your passive harmonic filter at the bottom, you're back to having sine waves, but you can see at the top with the clean power VFD that you have these sine waves in both voltage and current without any filter integrated. You're also seeing a better power factor, so that's in green at the top. You have almost unity power factor maintained by the clean power VFD without any filter. In terms of harmonics result, you can see your high harmonic content from your standard 6 pulse without filtering. And you can see that both the passive harmonic filter and the clean power VFD reaches to go below 5% harmonic at full load. Now, as I mentioned, this is a test in a lab with a very stiff grid. So in your typical environment, you actually might get below 3% harmonics at full load. You can also see the result in terms of voltage total harmonics distortion. This is the harmonic distortion that the utility is interested in because that's what is polluting beyond your grid. And you can see here that the clean power VFD in green actually outperforms both, of course, the standard drive, but even the standard drive with a passive harmonic filter. Now you could ask me, okay, that's fine for a standard drive with external filters. What about these integrated low harmonics drives? So in this case, you can have a multi-pulse drive. You can also have a active front end drive that integrates an active rectifier instead of the bridge diode bridge. And you also have these matrix architecture, which are AC to AC. Let's first talk about the active front end. Typically, in a active front end drive, they are focusing only on the first 50 order of harmonic. So this is the portion that is on the left of that red line. But everything that is on the right, so beyond the 50th order, is ignored by an active front end because there's this kind of blind spot between EMI zone and harmonic zone that is not regulated. So that's where you'll typically see manufacturers hide those higher order harmonics, and you can clearly see them in this signature of a leading active front end. And contrary with the clean power VFD, not only can you see even visually that your harmonic content is lower for the first 50 order, but you don't have that blind spot of hidden harmonics. So this already is an advantage of our drive compared to other active front end. Now, if we talk about the matrix architecture does not have a DC bus. So that exposes potential issue. If you have a disturbance on the grid, that will go directly to the motor on one side. And on the other side, because you don't have that DC bus, you don't have that potential boost. So you're limited to an 85% voltage output, which can be problematic in some cases, and certainly in long cable application, which is of interest to us today. But in all of these cases, they are still PWM-based solutions. So on the motor side, you will have pulse width modulation impacting the motor. And just visually, we can see if we take the same signature, not from the grid, but from the motor side, you can see the difference between a PWM type output harmonic content on the motor side and what SmartD delivers. And it's that motor side actually that enabled us to win a low harmonics deployment in data center where it was mandated to have a choke on the motor side because SmartD did not need that. We could offer both the low harmonic solution and the simplicity of not having any choke on the motor side. So that gave us a smaller panel and a simpler panel and ultimately won us the job. Now, let's look at this motor side because I mentioned harmonic, but it's not only harmonics. There are multiple things going on when we have this pulse width modulation. Um, Again, I'm not going to spend too much time because I assume everyone is already quite knowledgeable about this topic. But the pulse width modulation is the way you create this variable frequency signal in current. So you're doing these high-speed pulses, typically between 2 and 8 kilohertz, switching in a IGBT-based drive. So high switching pulses, and with that, depending on the duration of each pulse, you're able to recreate a pseudo signal in current. However, because of these high speed pulses, you are generating harmonics, and we've seen it in the other graphs. It's a much more messy distribution of harmonics. And just like you have on the grid side, the main impact of harmonics on the motor side is overheating. So your motor is overheating. It needs to dissipate those harmonics in a way or another. So heat, vibration, noise. And you could mitigate that if you really wanted to remove that. You'd have to go to a sine wave filter, as we've seen in the lab results. Well, actually, we haven't seen them. We're going to see them on the next slide. So here you have it. If you really want to go and remove all of that harmonics in the signal, you can see it here. The output of the clean power VFD is pure sine waves, both in terms of voltage and in terms of current. Your typical drive, you can see clearly the PWM in terms of voltage, and you can see how your signal in current is a pseudo sine wave, but you have this choppiness because you can see actually the different pulses there. And to get the same kind of result, you really need to go to a sine wave filter. So short of that, and of course, I don't know of anyone who puts a sine wave filter purely for noise purposes, although actually that's not true. I know one job where that happened. You won't typically do that, but that's the only way to really remove that issue. And if you compare the impact of our clean power VFD with a standard drive, PWM drive, you're going to measure about a 10% difference in temperature. And, we ironically deploy drive to preserve motors so that they don't get the high current peak when you start your motor from a contactor. But in the same time, you're inducing other problems that are actually reducing their lifespan. And temperature is certainly one of the key elements here. By having a higher running temperature, you're actually reducing the lifespan of the motor. And so by going with a clean power VFD, you're going back to the intentional original lifespan for the motor. So we can monitor this in the lab. You saw Roger's video also shows the sound level. We also see that when we go in the field. And so this is a retrofit that we did in a pump station in a municipality about 100 kilometers north of our office. And the interesting thing is not only can you see the different signal quality between our drive, but there's another drive just beside that is a standard drive on the other pump. And so you can see the signal quality, but you can also hear the difference, where in that case, you almost had a 15 dB difference in sound. And this is something that very often people will tell us when they first start up the clean power VFD is, are you sure your drive is working? I can't hear the motor. But really that is the element you are perceiving of the damage that is, the silent damage that's ongoing in your motor. In the meantime, in this case study, let me mention also that this is great. We deliver silence, we deliver clean sine waves, but we also deliver your efficiency you're expecting out of a retrofit. So you really have the opportunity to retrofit more easily and get that full ROI without the complication. Now, that's the first item that comes from the PWM. harmonics, let's look at the next one, which is voltage spikes. So on each pulses that is coming out of the VFD, you have a spike at the rising edge of the signal. And this problem actually increases as you have longer cable, as I'm sure all of you know. And you have a reflected wave impact where as you have a wave hitting the motor, it gets reflected back and can be combined with an incoming wave. And so you can have your spikes, not only the small spike at every leading edge, but it can get amplified. And the longer the cable, the bigger the problem. And so that not only damages potentially the cable, but also the motor insulation. And so typically, this is why we're going to mandate inverter duty motors. We're going to mandate higher voltage rated cables, and we're going to, depending on the length, require to have a choke, a DVDT filter, or a sine wave filter. And so if we actually go back to the lab, we can clearly see this is with a 480 volt unit, 500 feet of cable, that if you don't do anything with 500 feet of cable, you're going to get near 1800 volt of peaks, of voltage peaks, definitely higher than what your motor and your cable is rated for. On contrary, you can see how you're really delivering a very constant voltage through the clean power VFD, which is essentially equivalent to the sine wave filter. And someone could point out that, well, Simon, the clean power VFD is a little bit higher than your sine wave filter equivalent. And that's true, actually, because your sine wave filter is a big chunk of metal you're putting outside, you're inducing a bigger voltage drop. And certainly in the context of long cables, voltage drop is something you try to fight here. So this is with 500 feet of cable. If we go out in the field, we have this 1400 feet use case where you can see how you've got the pumping station on the left. On the right, you have the submersible pump and how the cable is going through the street. And so if you were to retrofit this, you are talking about a huge sum of money to pull out the cable that in this case was actually used cable, non-shielded, even potentially degraded. So you need to pull the pump, you need to pull all the cables, quite complicated. And this is a use case where they actually tried to put a standard VFD first, and it failed. So despite putting a VFD, putting filters, they had to pull it out. It was faulting nonstop. And on the contrary, they put the clean power VFD, no filters needed, directly connected to the drive. You get pure sine waves, go over those 1400 feet, no problems. And again, you've got a recipe for very quick ROI on a retrofit. You go from a contactor to a VFD, and you don't have to go through the hassle of mitigation and of what could potentially go wrong here. Now, we've talked about harmonics, we've talked about voltage spikes. There is a third killer here, which is common mode voltage. And you've seen it quickly in Roger's video. Common mode voltage is caused when your three phases are not perfectly balanced. If you have three sine waves, the sum of these three sine waves is zero. And so you don't have that common mode voltage. In the case of the PWM, those are square signal. They don't add up properly. And you have a non-zero common mode voltage. This can be actually above 100 volt, and then it hits the motor. The motor wasn't intended for that. You create a voltage potential, which induces a current in the motor, which now needs to get out of the motor, goes through the shaft, through the bearing, and that is what is causing your pitting, frosting, and flooding. Now, that you can it's you can put a choke there. You're not going to remove your common mode. The common mode is caused by the core of the PWM. And so all you can do is really try to get that common mode to go elsewhere. This is where the insulated bearing is trying to get not impact the bearings. The shaft grounding ring is trying to get the common mode to go through that ring instead of through the bearings. And the common mode choke will do what it can to get some through that choke instead of through the bearings. But you're really not addressing the root cause in all of these cases. And kind of case in point, you can see we go back to the lab, same setup. You can see the level of common mode current with just your drive. And even putting a sine wave filter is not addressing this because your sine wave is just getting some of the common mode current to go through that filter, but it's still reaching your motor. And so with the clean power VFD, you're actually, I can't say you're eliminating everything, but you're taking out 95% of that common mode current so that you don't have that issue. And we also observe that in the field. This is a case where we were approached by a customer that was having recurring bearing failures. And they really tried everything. They had chokes, they had DVDT, they tried replacing the motor, and nonetheless, they kept on having those bearing failures. And they then installed the Smart Clean Power VFD, and they got a new vibration analysis. So they really had a picture before and after. And that vibration analysis gave a complete new story where nearly 95% of the vibration acceleration was gone. The spike energy, nearly 90% of that was gone. But more importantly, they've stopped having those bearing issues. So we really see how we can go from the lab to the field, and we're seeing in the field the same benefits as what we see in the lab when we compare our clean power VFD, a standard drive, and a drive with filters. Now, what I'd like to address next is exactly how we bring that value to you guys. And this, at the core of our technology, is the silicon carbide MOSFET. And so the last revolution that I'd say powered the VFDs has been the IGBT, insulated gate bipolar transistors in the 1980s. That's really brought more reliability to the drive, scalability also to that architecture. And since then, VFDs have been riding the IGBT wave. Now, in the late 2010, so 2018, 2019, silicon carbide hit mainstream as it was adopted by EVs. And so from that moment on, production went up, and a lot of investment were done into silicon carbide. Okay, great, Simon. Thank you for telling us about silicon carbide, but why is it so interesting? Well, silicon carbide is part of a broader family of semiconductors, which are called wideband gap. They come also with gallium nitride. They both share some core values that make them very interesting. For one, they can switch at much higher frequency without any problems. I mean, IGBTs, you go above 8 kilohertz and you start derating them. Silicon carbide can hit 100 kilohertz, no problem. They have a higher power density. The higher switching frequency means that you have smaller passive components. They have lower losses. They have lower losses both on every switching losses, but also on what we call RDS on, when current flows through them. And so that means you're generating less heat for a same switching frequency. Now, you do need to be careful because the silicon carbide is switching from one state to the other much faster than your IGBT. And that faster switching generates more EMI and also actually causes more DVDT. So if you simply apply, whether it's silicon carbide or gallium nitride, if you apply these new material to your existing architecture, you're going to encounter problems, and you won't be able to use it as is. So this is where at SmartD we kind of had to reinvent the VFD. And so, yes, we wanted to have an active front end to get all those benefits of low harmonic and regen capability, but we use silicon carbide on it, and we use it at a super high switching frequency, so running at 105 kilohertz, using completely new modulation techniques. We integrated to that some self harmonic cluster cancellation. So this purely mathematical. Don't ask me a question on that. I don't really understand. Some much smarter guys on my team are doing that. Included that, used a 3-level architecture instead of your 2-level typical architecture. And what you have is a output of 210 kilohertz, but more importantly, we are able to reduce the size of the filter by a factor of 200. So, we say it's filterless for the user, but it's a little bit of a trick there because we actually have very small filters built into the drive. Now, I did mention that you need to be careful about the EMI noise because you're switching at such faster speed. And indeed, if you don't do anything, you're going to have an extra 20 to 30 dB of EMI. So what we did to address that is not only do we have smaller filters for the harmonics, but we combine that with our EMI filter. So it's kind of an all-in-one filter. And the end result is we have 70 dB reduction in differential mode and 80 dB reduction in common mode noise for EMI. What that means for you as you install one of our drive is really you don't need to think about any kind of filtering on the grid. So that is built in. The active front end takes care of that for EMI, and takes care of that for harmonics. Now, if we go on the inverter side, we apply the same recipe. So multi-level architecture reduces the steps and the amplitudes of the PWM built into the drive. We integrate a filter, an output filter that is also doubles as an EMI filter. And what's really important as we apply this filter is we would need to address the extra DVDT coming out of the silicon carbide. And so if you were not to do anything, and this is where I said you can use it in the existing architecture, an existing VFD architecture, well, what you get is a whole lot of noise. So someone, main manufacturer, takes the silicon carbide, puts it in their existing drive, they would get a bunch of garble to the motor and probably would kill the motor pretty quickly because of that extra DVDT. In our case, because we have these integrated filters, you get a sine wave at the output of the drive, and you get sine wave at the output of 500 feet, 1,400 feet of cables, you name it. We maintain the sine wave throughout that length of cable. So again, we take out the mitigation. So you don't need a sine wave filter. It's built in. Your motor runs cooler and quieter. You don't need to upgrade your motor for an inverter duty motor. You don't need to change your cable. You can use as is. It will work. And you don't need to think about how do I mitigate a common mode that will kill my bearings over time. We're reducing 95% of common mode directly out of the bat. So really, I love this picture. It's a great way to summarize what we do. We're going from mitigation to simplification. Take out these if, these buts, these, hey, my retrofit fails because of harmonics or because of the PWM output or voltage spikes. Just take that out. You don't need those external filters. You don't need those shaft grounding rings. You all have it built in the SmartD Clean Power VFD. And I mentioned it quickly, but our drive is also a fully 4-quadrant drive. So you're able to have full regen capability in the drive. You don't need a braking resistor. This is great on application where you can benefit from this where you really maximize your energy savings. And you also have that built-in DC bus so that you have that extra voltage boost on the output, and you have that protection from grid disturbance. So last section of the presentation, I'll give you a quick view of what the drive looks like in practice. We have a touchscreen HMI. This enables us to do a quick updates of the drive. So the drive can be fully updated through the USB port. You can kind of see it, it's there. In 5 minutes, you update the drive. If we add new features, new function, HMI gets updated. So you don't need to relearn button. It's very intuitive. You can read if there's an alarm. It's in plain English. Today it's multilingual, English and French, and we plan to support more language in the future. But you really have a ease of understanding with that touchscreen HMI. I/O, nothing much special to mention other than it is a pretty rich I/O drive. So you'll have all of your industrial I/Os there. Should be good for most of your applications. And your analog in can be programmed for either universal input or for a quadrature encoder. We also strongly believe in free or embedded communication protocol. So the drive comes with Modbus TCP and BACnet IP built in. We also have Ethernet IP that will be rolling out very shortly. And all of these are accessible without any additional board. Again, we don't want you to buy external filters. We don't want you to buy external communication boards. We believe everything should be built in. And last but not least, the drive can be fully programmed through a mobile app. The mobile app is available on Google Play and the App Store. If you search for Clean Power VFD, you can download it today and play around with it because you can do the setup offline. And it's pretty straightforward. Walk through the wizard and you should be good to go. Now, with that, you should be good to open your eyes to what are the opportunities out there. I mean, if I put it in a nutshell, any low harmonic opportunities, definitely good for our drive. Retrofit, probably the best bang for your buck because you're not adding any external filters, you're not changing the motor, not changing cables. We see great opportunities with a straightforward retrofit, and surprisingly, there are just so many motors still on contactors. So this is a huge opportunity. Anytime where you have lots of filters and is increasing the space, that's a good opportunity. And finally, I did mention also regen. So we do have 4-quadrant capabilities in the drive, so that's an opportunity you should keep your eyes on, open for. With that,